Okay, in this video, we continue with the we continue the recitation video with the topics focus on the volumes of revolution. So I will solve the problems that are related to the Washer method and the Shiranshu-Kochab method. So these are two formula you should know for the Washer method and Shiranshu-Kochab method. And most of the time, we're going to use the Washer method to to find the volumes of the objects that is obtained by spinning some regions around the x-axis. And we will use the Shiranshu-Kochab method to find the volumes of the objects obtained from spinning the regions around the y-axis. Okay, I mean, actually, there's no really the there's no. I mean, you can use the Washer method to find the volumes of the objects that are obtained from rotating some regions around the y-axis as well. But most of the time, this is for the objects with the y-axis. I'm sorry, this is the formulas for the objects spinning around the x-axis, and this one is for the objects obtained from spinning around the y-axis. This is most of the case. Okay, and if you don't really understand why we have these two formula, I suggest that you should go to lecture number 2 to rewatch the video so that you can have the better understanding about Washer method and Shiranshu-Kochab method. Okay, so let's go into the first problem. So in this problem, the question wants us to find the volumes of the solid obtained by rotating the regions bounded by y equal to 9 minus x squared, y equal to 0, and x equal to 0 about the x-axis. And like I said, in the recitation video, I just solved a similar question. So up here, I changed the function a little bit. Instead of 4 minus x squared, I have 9 minus x squared. But for your original problem, you should work with this function, 4 minus x squared. Okay. So, and I would say that when you have to do something about the volumes of revolution, I suggest that you should craft the function. You should craft the region to see to have the better imaginations, and then you can formulate your volume better. Okay. So over here, because you're spinning something around the x-axis, so I'm gonna use the Washer method. And for the Washer method, that means you'd have to, if you want to use the Washer method, you need to know four things. You have to know the lower bound, the upper bound, the upper function, and the lower function. Okay. So up here, the region is bounded by 9 minus x squared. The vertical line x equal to 0. Sorry, the line x equal to 0. The line y equal to 0. Okay, so this is the region that we are using to spinning around the x-axis. Okay, so technically you already know the upper function. The upper function is 9 minus x squared. This is the upper function, right? The lower function will be 0. Okay, this is 0. So the only thing you need to know is, we know the upper function, we know the lower function. So the only thing we need to find is the lower bound and the upper bound. So technically, this is the lower bound, right? This is a lower bound, and it's given by the value 0. So you need to find the upper bound. So I would say that the upper bound is this point. This is the upper bound. Okay, this is the upper bound. And to find the upper bound, you can pretty much say that the upper bound is the intersections between the curve 9 minus x squared and the line y equal to 0. Okay, so we need to find the upper bound. So firstly, we find upper bound. Okay, so I just simply let 9 minus x squared equal to 0 because the upper bound is the intersections between the curve 9 minus x squared and the line y equal to 0. So I let 9 minus x squared equal to 0. Okay, and I have x squared equal to 9. So I have x equals to 3 or x equal to negative 3. And the point is we just focus on the intersections between the curve and the lines on the right side over here. So I just take the values 3, and the values negative 3 is not contained inside the regions. Okay, so I don't take this one. Okay, so now we know the lower bound. The lower bound is 0. We know the upper bound. The upper bound is 3. The upper function is the upper curve, 9 minus x squared. The lower function is y equals to 0. Okay, so we have volume equal to the integral from 0 from 0 from 0 to 3, from 0 to 3. The Western method, we have pi multiplied by the upper function square. The upper function square will be 9 minus x squared. So I have 9 minus x squared, and then I square it. Okay, and subtract the lower function square. The lower function is 0. Okay, the lower function is 0. So I have 0 square. Okay, dx. And now I will simplify it. Firstly, I bring pi to the front. 9 minus x squared gives me 81 minus 18x squared plus x to the power of 4. 0 squared, just 0. So I don't write that again. Okay, and now you use the power rule. You have 81x minus 18x cubed divided by 3 plus x to the power of 5 divided by 5. You evaluate at the lower bound and the upper bound. Okay, and you just need to evaluate your antiderivative at the lower bound and the upper bound, and you find a difference. So you pretty much have pi times 81 times 5 minus 6 times 5 cubed, because 18 divided by 3 is 6. And you plug in 5, you have 5 cubed plus 5 to the power of 5 divided by 5. And when you plug in the lower bound, you just simply have 0. So this thing is 0, this thing is 0, this thing is 0. So you can use your calculator, simplify this thing, you will have the final result. Okay. Okay, in the next the question wants us to find your volumes of the solid obtained by rotating the regions bounded by the curve 2 minus x squared and the curve y equal to x squared. Okay, and you have some regions, and you're gonna spin the regions around the x-axis to obtain the solid. And like I said, I just solved a similar question. So instead of having a minus x squared, I have 2 minus x squared. Okay. Okay. So now the point is, if you want to use the Washer method, you need to know the lower bound, the upper bound, the upper function, and the lower function. So this is the upper function. So we know the upper function. This is a lower function, and it is given by x squared. The upper function is given by 2 minus x squared, and the lower function is given by x squared. The only thing you need to know is the lower bound and the upper bound. So you can pretty much see that the lower bound and the upper bound over here, they are just the intersection between these two curves. So firstly, we're gonna find the intersections, or we find the bound. Okay. Okay. To get a bound. Sometimes the question will give you the bound. But if the question don't give you the bound, you have to find the intersection between curves that are given in the questions. Then you can find the bound. Okay, so the intersection is the solution to the equation 2 minus x squared equal to x squared. Okay, they are intersection between these two curves. So you just simply let these two curves equal to each other. And you have 2 equal to 2 x squared. Okay, I'm adding x squared both sides. So I have x squared plus x squared, give me 2x squared. This one gonna give me 1 equal to x squared. So that means I have x equal to 1 or x equal to negative 1. Okay, so this a negative 1 will be the lower bound and 1 will be the upper bound. Okay, so we can now start writing your formulation for the volume. So the volume is the integral from negative 1 to 1, because the lower bound is negative 1 and the upper bound is 1. To use the Watson method, we have pi multiplied by the upper function square, subtract the lower function square. Okay, the upper function is 2 minus x squared, so I have 2 minus x squared and I square it. The lower function is x squared, so I have x squared and I square it. Remember that you have to subtract the lower function square. In this scenario, your function is x squared and you have to square it. Okay, be careful with this one. Okay, and now you can just need to simplify the function inside your integral, and then you can use the power rule. Firstly, we can bring pi to the front. Okay, and 2 minus x squared gonna give me 4 minus 2x squared plus x to the power of 4. Subtract x squared and you square it, you have x to the power of 4 as well, dx. And then you have the integral from negative 1 to 1 of 4 minus 2x squared, because x to the power of 4 cancel out with x to the power of 4, dx. Okay, and then we use the power rule. We have 4x minus 2x cubed divided by 3. You have to plug in the lower bound and the upper bound. Okay, you plug in the upper bound. You have pi times 4 times 1 minus 2 times 1 over 3. Subtract pi 4 times negative 1 minus, let me move this thing to the left a little bit. Okay. Plug negative 1 with 2 times negative 1 cubed divided by 3. And then you can use your calculator to simplify the calculation. Okay. Okay. Like next, we go into the cylindrical shell method. And most of the time, we're going to use the cylindrical shell method to find your volumes of something that is obtained by spinning some regions around the y-axis. Okay, and instead of solving the original questions, I'm solving the questions where the curve is 1 minus x. So this is the curve 1 minus x. Okay. Okay, and the same thing. This is the cylindrical shell method. I mean, this is the method. I would say this is the formulation for to find your volumes of the object spinning some obtained by spinning some objects around the y-axis. But if you're spinning the regions around some other vertical line, then you have to update the formula. But most of the times, you will use this one. Okay. Okay. And like I said, you have to figure out what do you need to formulate your volume. You need to find the lower bound, the upper function, and the lower function. So in these questions, you already know the lower bound. The lower bound is the line x equal to 0. So you need to find the upper bound. And again, the upper bound is just the intersections between the curve and the line y equal to 0. So firstly, you find the intersections to get the upper bound. Okay, and you just simply let 1 minus x squared equal to 0 because this one is the intersection between 1 minus x squared and 0. So you have x squared equal to 1. That means you have x equal to 1 or x equal to -1, and -1 is this point. And this point is not contained inside the region, so we don't really care about this one. We just take 1 as the upper bound. So once you get the upper bound, you can start writing your formulation for the volume. So the volumes of the objects when you're spinning these regions around the y-axis will be the integral, the lower bound, upper bound. The lower bound is 0, the upper bound is 1. So you have the integral from 0 to 1. Okay, they multiply by 2 pi x. So you have 2 pi times x times the upper function, 1 minus x squared, subtract the lower function, which is 0. Subtract the lower function, which is 0. Okay, and now we simplify. We have, I bring 2 pi to the front because it's constant. Okay, we have x times 1, give me x. I have x times x squared, give me negative x cubed dx. Okay, I have 2 pi. The integral, the antiderivative of x is x squared divided by 2. The antiderivative of x cubed is x to the power of 4 divided by 4. Okay, and we need to evaluate the antiderivative at the lower bound and the upper bound, and we'll find a difference. So we simply plug in 1. We have 1/2, 1 squared divided by 2, minus 1 to the power of 4 divided by 2, divided by 4, I'm sorry. Subtract 2 pi, and you plug in 0, you just have 2 pi, 0, right? Because you plug in 0 to here, and you plug in 0 into here, you have 0 minus 0, you just actually have 0. So therefore, you have 1/2 minus 1/4 gives you 1/4, okay? So you have 2 pi times 1/4, what is pi over 2. So this is the volume, so the objects when you're spinning these regions around the y-axis, okay? Next, you have to find the volumes of the solid that is obtained by rotating the regions divided by the function 2x, the line 2x, and the curve y equal to x squared. So this is the pinky regions that I have over here, and you're spinning this region around the y-axis. Okay, and again, we're gonna use the sequential method. In this question, you are given the lower bound. You are given the upper function and the lower function. Okay, therefore you just need to find the bound, the lower bound and the upper bound. The low and this question does not give you the bound, so you just simply find the intersection between the upper curve and the lower curve to get the lower bound and the upper bound. Okay, so we find the first step, we find intersections by simply let x squared equal to 2x. Okay, therefore we have x squared minus 2x equal to 0. I just move 2x to the left side. Therefore I have x minus 2 equal to 0. Therefore I have x equal to 0 or x equal to 2. Okay, so this is the lower bound. This is the upper bound. This is 2. Okay, and now we can use the series quotient method to find the volume. So volume is the integral from the lower bound to the upper bound. You have 2 pi times x times the difference between the upper function and lower function. So the upper function is the line. You have 2x. The lower function is x squared. So you have 2x minus x squared dx. Okay, and you have that brings 2 pi to the front. The integral from 0 to 2. X times 2x gives me 2x squared. X times x negative x squared gives me negative x cubed. Okay, and then we just need to use the power rule to find the antiderivative. So I have x cubed divided by 3. Sorry, 2x cubed divided by 3. Subtract x to the power of 4 divided by 4. And you need to evaluate the antiderivative from 0 to 2. Okay, so I believe when you plug in 0, it's not a big problem. You just simply have 0, and then you plug 2. So we have 2 pi times 2 times 2 cubed divided by 3 minus 2 to the power of 4 divided by 4. Subtract 0. I mean, subtract 2 pi times 0. Okay, but the point is, when you plug in 0, you have 0 minus 0. That's why I write it down at 2 pi times 0. 2 pi. 2 times 2 2 times 2 cubed give me 16 divided by 3 minus 16 divided by 4, and you can use a calculator to simplify this. Okay, so we're done with the problem that are related to the volumes of revolution. Okay, and you should try to solve the original problem with the original function that you have, but the idea is pretty similar. Okay, and I will see you in the next video. We're gonna discuss the problem that are related to the integration by part.